video 18 of the master course, Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is the Ehrenfest theorem. In lecture 33, we looked at the dependence of an expectation value on the strength of an external field. And in chapter 3.4, on the second derivatives of the energy, we actually took then the derivative of such an expectation value with respect to a component of the field. In this section, we want now to look at the time dependence of an expectation value, and we will study it by taking the derivative with respect to time of such an expectation value. So here we have an expectation value where we have a time-dependent situation, so our wave function depends on time. And we will take the derivative with time now. Now again, like in all the cases so far, the integration here in the expectation value is of course an integration over the spatial and spin coordinates of the electrons, whereas we take here the derivative with respect to time, which means that we can interchange the integration and derivative. And again, here we have three terms. We have a product of three terms, and therefore we have to use the product rule, which means that we are going to get three terms. One where we take the derivative of the wave function here in the bra, and the last term where we take the derivative in the ket, and here in the middle one where we take the derivative of our operator with respect to time. Now let's assume that we are in the situation where our operator P here is not depending on time, which is in a way the normal case. So what we have to do now is we have to take the derivatives of the wave function with respect to time. And the question is, where do we get information on this? Well, the answer is very simple. We get this from the time-dependent Schrödinger equation, because the time-dependent Schrödinger equation is nothing else than an equation which tells us what the time derivative of the wave function is. So we can use the normal time-dependent Schrödinger equation here for the ket, and of course we can rewrite it also to be valid for a bra wave function. So we can replace the derivative of the wave function with time by applying the Hamiltonian of the system to the wave function and then multiply with minus I divided by h. And correspondingly here for the wave function in the bra, of course we have to remember that everything in the bra is complex conjugate, so we have to complex conjugate the I here. Now we can insert this one over here and that one over there, and you can see both terms are very similar. Here we get h times p, and here we get p times h, and then we have a change in sign, so we can combine the two in one commutator, as I have done here in the last expression there, which means in the case of an operator which does not depend on time, the Ehrenfest theorem tells us that the derivative of the expectation value of this operator is nothing else than just the expectation value of the commutator of this operator with the Hamiltonian. Now in derivation of the Ehrenfest theorem, apart from simple mathematics, we only have used the time-dependent Schrödinger equation. This implies that the Ehrenfest theorem, this equation here, essentially contains the same information as the Schrödinger equation. And we can therefore use the Ehrenfest theorem in place of the Schrödinger equation when we want to look at the time dependence of a system. And precisely that we will do in the third part of the book when we derive approximate methods, where we will apply the Ehrenfest theorem to operators P which govern the time dependence of the system.